Okay, we are going to move on to example 15. We did example 13 earlier on. 14 are all done for you. So we are going to move on to example 15. In this question, you want to solve this integration problem using the given substitution that u is equals to root x. So how do we do this method? From here, right? From here, we want to actually replace. We want to replace the dx as dx du and then du, right? So this becomes 1 over 1 plus square x. What is dx du equals to? From here, right? X is equals to u squared. So dx du is equals to 2u. I might want to just replace this as well. Might as well. This is u, and then dx du I replace it with du, 2u, sorry, 2u, right? So then I get 2u over 1 plus u du. And to integrate this one, we need to do this using, if you like to call it long division. So this gives you minus 2. If you perform your long division, I think you should be getting this. Alright? And then you integrate them individually, you get 2u minus 2 ln of 1 plus u plus c. Because this is an infinite integral, you must put back the original variable, which is x. So in place of u, I now put it in as square x 1 plus square x. Right, that's example 15. Let's do example 16. Example 16 also is to do by substitution. This one involves trigo, x into 1 minus x squared dx. In this question, the recommended substitution is to let x be equals to sine theta. Okay. So how do you do the replacement? In place of x, I put as sine theta, and this gives me 1 minus sine square. In place of dx is dx d theta. In this case, it's cos theta, and then d theta. Right. So bear in mind, I have replaced my dx as dx d theta. So upon cancellation and tidying up, it left with cosecant theta d theta. And then there's a known integration formula for this integration. It is minus ln cosecant theta plus cotangent theta. Now you put back the original variable in terms of x. So this gives me ln of, if x is sine theta, cosecant theta is 1 over x. Okay, if x is sine theta, you can draw a simple diagram to help you to see things better. This is theta, this x, and this 1. So this length here will be x squared minus 1 squared. So cotangent will be equals to square of x squared minus 1 over x. Cotangent is adjacent over opposite plus c. So this is what you're going to have for this question, right? Okay, so using the known integration formula for cosecant, I get this line, and then I just replace, and then I'm done really. And that's example 16. Okay, with this, we're going to move on to integration by parts. Right, you probably learned this in the lower year, how to perform integration by parts. I hope you still remember. Okay, there are various formulae that people have given to you for by parts. I think. Okay, let's see what the notes provides you. Okay, for the notes, right, it provides you with this formula by parts. Okay, by parts. Formula given the notes is okay. Integration of u dv dx equals to uv minus du dx v dx. Right. This is the formula given to you in your notes. Okay, using this by parts formula, we can then try to actually do a few examples. In example 17. In example 17 part 1, you are given this question, x cos of 2x dx. How do we do this question using by parts? You want to choose this to be your u, and then choose this to be your dv dx. Right? So according to the formula, it's going to be uv. If this is a dv dx, then your v will be sine 2x over 2 minus du dx will be 1, and then again to get the v is sine 2x over 2. If you do by parts correctly, you will realize that in the first stage, right, you do integration twice, right? Integrate this one once, again once, right? And your differentiation you do only once. This one is not differentiated, just leave it as it is, kept as it is. Here is differentiated. So now I'm going to have x sine 2x over 2 minus become plus cos 2x over 4 plus c. So this is 17 part 1. We have done it by parts. Let's do 17 part 2. 17 part 2, you have 2x tangent inverse x. Let me write this way, tangent inverse x and then 2x. Okay, why do I write this way? Because I just want to be consistent. This is the term to be so-called differentiated. This is actually the u, right? This is the u, and this is actually your dv dx. So according to the formula is u. Okay, if this is dv dx, then v is x squared, right? Then you got to differentiate the u. Differentiating this is 1 over 1 plus x squared, and then integrating the 2x, right, is just x squared. Okay. Then you can tidy up this as x squared tangent inverse x. To integrate this one, you can do so-called long division to become this. Now you just perform a simple long division. Upon integrating, right, this should give you minus x plus tangent inverse x plus c. Right. Oops, you can't really see. Let me just adjust a bit. Okay, you can see now. The below part. Okay, you can see now. Right. So this is actually by parts for number 17, part 2. Let's look at 17, part 3. Okay, let me create space for 17, part 3. Let me erase off there. Okay, 17 part 3. Integrating sine inverse of x dx. Okay, for this question, you probably already know the trick. All you can do is we are going to actually see this as u, and then see your v as, so I see your dv dx as 1. Okay, then the formula goes u v is going to be x minus integration of du dx, and then v. Right, so this gives you x sine inverse x minus, okay, to integrate this one, right, I'm going to rewrite this thing as like that. What am I doing here? I'm trying to rewrite it in this manner. Writing this manner allow me to use the formula that I told you from page 2, remember? On page of the notes, I asked you to write down some formula, right? This is actually formula, the third formula. This is f prime divided by the square root of fx. So then I can get this to be, okay, twice of the denominator. So at the end, I tidy up this to become simply like that. Right, this is example 17, part 1, 2, and 3. Okay, so up to this point, this is something that is so-called bread and butter. Okay, I hope you can see the bottom part. Yep. Okay, let me just see. Okay, right. Okay, up to here is just things they've learned previously, right? Okay, so maybe we'll stop here. We'll continue on reduction formulae on the next video.